Welcome back, physics fans. Today we're going to tackle a problem dealing with torque and static equilibrium. If you have any questions about those specific topics, please address them with your instructor or watch the instructor-provided video prior to continuing this video. Before we get into the solution, let's go ahead and take a look at the problem statement. Cadet on a board. You are given a wooden board, a 2x4, sitting on top of a lab bench. Less than 1/2 of the board's length is hanging over the edge of the bench. One of your classmates is standing on top of the portion that hangs over the edge of the bench. Derive an algebraic expression for the distance from the axis of rotation, in other words the edge of the bench, to place a countermass that balances the cadet on the hanging portion of the board. Your final expression should be in terms of cadet mass M1, cadet distance from edge of bench R1, countermass M2, countermass distance from edge of bench R2, mass of the board MB, and length of the board L. Since we'll be applying forces at some distance from an axis of rotation on the board, we'll need to consider torque. Additionally, because we'll be applying multiple torques to our wooden board, we'll need to consider Newton's second law for rotation. The task that we've been identified to solve is explicitly stated in the problem statement, and that is to derive an expression for R2. R2 being the variable that we'll use to define the distance from the axis of rotation on the wooden board that we'll need to place a countermass to balance the cadet. Now let's talk about the physics involved in this problem. Because we're dealing with torque, a good place to start is the definition for torque, which states that torque is equal to the cross product of some displacement from our axis of rotation and an applied force vector. Additionally, Newton's second law for rotation states that the sum of all external torques on a system is equal to the product of the rotational inertia, I, and the angular acceleration of the system, alpha. Here you can see a drawing of our problem. We have the 2x4 drawn with our cadet of mass M1 and our countermass of mass M2. The mass of the board is labeled as MB. Here we have identified our axis of rotation for the board given by that triangle. That is our edge of our lab bench. We have the distance from the axis of rotation to the cadet mass, R1, as well as the distance from the axis of rotation to the countermass, R2. Finally, we have the total length of the 2x4 wooden board labeled as L. In the problem statement, we're creating an expression that identifies R2 in terms of given variables. Those given variables being M1, M2, MB, R1, and L. Before we can proceed with a solution, we'll need to make some assumptions in order to solve the problem. Because we're not explicitly given any information in the problem statement on any external forces acting on the board countermass cadet system, we need to assume that gravity is the only external force acting on the system that is not specifically identified in the problem statement. Now we're ready to solve the problem. As with all Newton's second law problems, a good place to start is with a free body diagram, which is what you can see here. I've isolated my body of interest, being the 2x4 wooden board. I've labeled all appropriate dimensions on my body. I have the mass of the board MB, and I have the length of the board L. Additionally, I have the distances from the axis of rotation to the cadet mass and the countermass of R1 and R2 respectively. The next step in drawing a free body diagram is to draw all forces exerted on the body. So here I have the gravitational force, which is really exerted as a normal force between the cadet and the board, oriented in a downward direction with magnitude m1g. Additionally, we have the gravitational force, which is also exerted as a normal force between the countermass and the wooden board in a downward direction of magnitude m2g. Gravity acts on the center of mass of the wooden board, so we can see that our gravitational force on the wooden board itself is oriented at the center of mass, pointing in a downward direction of magnitude mbg. Finally, we have to consider the normal force exerted between the axis of rotation, in other words, the edge of the lab bench, and the wooden board itself. So you can see that normal force oriented here at the axis of rotation in an upward direction. It's perpendicular to the surfaces in contact, being the edge of the lab bench and the wooden board itself. The final step in any good free body diagram is to label your axis directions, which you can see I've done right here. So we'll go ahead and we'll call the horizontal direction in this problem the x direction, and we'll call the vertical direction in this problem the y direction. Additionally, we'll label any counterclockwise rotation of the wooden board to be positive. Now that we've completed our free body diagram, we're ready to apply Newton's second law for rotation. Again, Newton's second law for rotation states that the sum of the torques exerted on a system is equal to the product of the rotational inertia, I, and the angular acceleration, alpha. Let's start on the left-hand side of the equation and sum the torques that are being exerted on our system. We'll start with the countermass. Here we have the force being exerted by the countermass, m2g, crossed with the distance from the axis of rotation, r2. That term is positive because in the absence of any other torque on the system, it would induce a counterclockwise rotation of the wooden board. Moving along, we have the force exerted by the gravitational force on the wooden board, crossed with the distance that force is exerted from the axis of rotation, given by this quantity right here. So this is simply the distance from the axis of rotation to the gravitational force exerted on the board, expressed in a way that uses the variables that will be given. That term is also positive because, again, in the absence of any other torques on our system, it would induce a counterclockwise rotation of the wooden board. Finally, we have the force exerted by the cadet, m1g, crossed with the distance that force is exerted from the axis of rotation, r1. That term is negative because in the absence of any other torques on the system, it would induce a clockwise rotation of the board. Now that we've applied Newton's second law, algebra takes over. We're attempting to isolate our objective variable, r2, in terms of all given quantities, which is exactly what you see here. We arrive at a solution for r2 in terms of all given quantities. The final step of the problem-solving process is to check our work. When we perform dimensional analysis of the right-hand side of the equation, we determine that r2 is measured in base SI units of meters, which makes sense for a distance measurement. Since the problem statement explicitly states that we should create an algebraic expression, we don't need to concern ourselves with the number of significant figures in our solution. Finally, if we apply some test values to our given variables and plug them into our expression for r2, we can determine that r2 is calculated in a value that makes sense when we reference our free body diagram. So it stands up to scrutiny, and our solution meets all three of our check criteria. So I can talk the talk, but can I walk the walk? Let's head on over to the lab and find out. The board that we'll use for this demonstration is approximately 4.31 kilograms, with a length of 2.53 meters. I have a mass of 83.5 kilograms, and I've acquired 14 kilograms of countermass. The board overhangs the lab bench by approximately 0.4 meters. When we substitute these numerical values into our previously derived solution, we calculate that the countermass should be located at a distance of 2.12 meters from the edge of the lab bench, which is where the countermass is currently located. Let's see if our solution stands up to scrutiny. And there you have it, physics fans. If you have any further questions, please direct them to your instructor. As always, may drag be negligible and the net force be with you.